Language models have a long history. Started out with simple statistical models, but over time has turned into deep large neural networks that we see today. A language model in a nutshell predicts the current word given the history of words that it has seen. For a simple sequence like we ran away from the bank of the river, we will predict any word given the history of words. So we predict the word bank given the preceding sequence we ran away from the that we have seen. So let's start with the simplest language model, that is n-gram model. With an n-gram model, we first pick a value of n. So let's say we pick an n of 2. Then we look at previous n tokens to predict the next token. So we look at we ran and predict away, ran away and predict from, away from and predict the, and so on and so forth. So let's create a table to track these transitions in. What we want to track is what context we saw and then what the next word occurred. To make things simple, let's assign IDs to each of our words. So let's say we assign we the ID of 1, ran the ID of 2, away the ID of 3, and so on and so forth. And whenever the same word occurred as before, we'd assign it the same ID again. So we see the again, so we'd assign it 5. In the context, we'd record what are the pairs of words we see every time when we try to predict a word. So that'll be 1, 2 for we ran away, 2, 3, and then from the, that is 3, 4. Those are the context we see each time we try to predict the next word. For the next word, we simply look at the context and what the next word appear. So for 1, 2, the next word was 3. So we'd record that. Similarly, for 2, 3, the next word would be 4. So we'd record that as well. And then for 3, 4, the word would be 5, and then so on and so forth. We'll call this our transition table. Next, we want to convert this transition table into a probability table. We want to be able to use this probability table to then generate a sentence. We would look at a context and then find out which next word has the highest probability. So our probability table will have 3 columns for context, next word, and probability. And we'll copy over all of the unique triplets of context and new word that we have seen into this table. To calculate the probability, then we simply find out for any given row, let's say 1, 2, and 3, we find out how many times 3 occurred after 1 and 2, and then how many times 1 and 2 occurred in our corpus overall. And then just divide one by the other, and that gives us the probability. Let's say in this case, 80% of the time, 3 occurs after 1, 2. So the probability would be 0.8. For another pair, let's say 4, how many times does that occur after 2 and 3? Let's say that's very small, like 1%. That will be our n-gram table that we can then use to generate sequences. We just have to give it the start word, and it'll keep looking at the last 2 words to generate next word using the probabilities. Next, let's look at some of the problems with this modeling approach. One of the biggest problems with n-gram models is that it's not able to scale. If we look at the relationship between model size and vocabulary, we see that model size exponentially grows as our vocabulary becomes larger. If we take our example of n as 2 and vocab of 8, we can have 64 items at max in our n-gram table. However, if we use a more realistic value like n as 4 and vocab size of 5,000 words, it quickly becomes too large. Granted that some of the combinations will not occur and it will be sparse, but it's still a large number nonetheless. Next up, let's look at recurrent neural networks and how they solve some of the problems that were there with n-gram models. With recurrent neural networks, you don't have to maintain a large table of transitions. Instead, the model itself has an internal parameter called state, which will be used to generate the next word. Let's take the same sequence that we were using before. We ran away from blah, blah, blah. Previously, we were looking at we ran and then predicting away. However, we'll not do that anymore. We would just take the current word, which is we, take that, and the state that is internal to the model and then use that to predict RAN. Expressing this model mathematically is very simple. We have wx vector which gets multiplied with the current item vector. We have a wh vector which gets multiplied with the hidden state vector which is transmitted from the previous time step. Adding both of these up gives us a state vector called ai, and then ai gets finally multiplied with wy to give us the final next word. And since this is a deep neural network, we can add sigmoid activation to both of these states. If you find this a little bit complicated, let's look at the unrolled version of this diagram to understand this in further detail. In this unrolled version, we can see that our hidden states start with a special start token, and then we input our first word V to predict RAN. Then we take the hidden state from the previous step and give the input RAN to predict away. Then we give the word away and next predict the word from, and so on and so forth. To train this network, we need to just generate pairs of tokens from our training data. So we just need to keep track of the previous token and the current token. For our example, these tokens would be start and the word V and the word RAN and the word away, and then so on and so forth. We then use these pairs of tokens to train our network. We have to feed these pairs into the network in the exact same order because we need the hidden state from the previous time step. This is a problem as it hurts parallelization, which slows down the training a lot. After training each block of text or sentence, we reset the hidden states. Another problem with recurrent neural networks is that they learn using gradient descent, which backpropagates the loss through many layers to update the weights. As these gradients multiply across layers, if the values are very small, they start approaching zero very quickly. But if it's too large, it approaches infinity value. This problem is widely known as vanishing and exploding gradients, which makes training of these networks on large corpus of text very hard. Next up, we have convolution networks. Although convolution networks are not widely known to be used as language models, we can use it to generate text. And transformers, which are state-of-the-art language models today, borrow a lot of ideas from convolution networks. Just like previous models, in convolution network also, we feed in n previous word to predict the n+1th word. As convolution networks cannot handle variable size inputs, we'd have to set an n value before training, just like we did with n-gram models, and then generate the training data. However, as there is no hidden state vector like with recurrent neural networks, we can parallelly train on these examples. Then based on the convolution size, the model looks at parts of the input sequences and aggregates these information to predict the next word. However, the convolution size limits how many words the models look at in one go and selectively attends to only those words in the sequence. Another problem is that once the convolution is learned, even if it finds those same words in a different context, the model won't be able to differentiate, as convolution filters are translation invariant. This is a good property for image recognition, but not so great for language modeling. Finally, let's summarize the models and issues that we have seen with those models before we jump into transformers, which is the current state-of-the-art model. With n-gram models, the biggest issue is their scale and poor generalizability. With the recurrent neural networks also, scale is a challenge as parallel training is not possible, but gradient issues are a bigger limiting factor. With convolution networks, their selective attention to parts of the sequence and convolution filters being translation invariant are the biggest problems. In the next one, we'll look at the transformer architecture and how it solves each one of these problems.